Class, good day. So this is for the introduction for the principles of steel design. So first part, I design and analysis of tension members. So this aims to give you an overview of the properties of structural steel design methods. So we have two design methods. That is the allowable strength design, or the ASD. Then the load resistance factor design, or the LRFD. And the design code provisions for steel sections subjected to tension. So it will enable you to analyze and design tension members, whether bolted or welded. So these are the two types of possible connections for structural steel members. It will also provide you a step-by-step procedure on how to design tension members using LRFD and ASD design method. Okay, so again, for the first part, this is the analysis of a tension member. So we are to determine the nominal and the strength design of a tension member. So we have three considerations here. The number one is the gross section yielding. In some references, we can abbreviate this one as the GSY. So the gross section yielding. So we are considering, class, the gross section yielding due to possible excessive elongation of the tension member. So we have for the nominal strength, that is the P sub n, Fy, the yield stress, multiplied by the area gross. Then for the design strength by LRFD, that is the P, a reduction factor P, which is equal to 0.9 for tension members, is equal to Fy times Ag. Or we can have it as, if you say a design strength, that is the ultimate P sub U, is equal to P multiplied by the P sub n, or we can have it as a P Fy multiplied by the area gross. Then for the, this is for the ASD, the allowable tensile strength. So we have, that is the P sub n over omega. So the value of omega will be equal to 1.67. So this is for 0.90, a reduction factor, while for the 1.67, this is the factor of safety. Okay, so we can write for the allowable tensile strength, that is the same as the PA is equal to the P sub n divided by the factor of safety omega. So anyway, for a safe analysis, we can write our equation in this manner. So you have P sub U should be less than or equal to P times P sub n, less than or equal to be safe. So P sub A should be less than or equal to the P sub n divided by the omega. That is for the GSY, or the gross section yielding. Then for the tensile rupture strength, if you say tensile rupture, that is the same as the breaking strength of a tension member. So this time we have for the nominal strength, that is the P sub n Fu times AE. Or we can have the design tensile strength for LRFD, that is P sub n. So our reduction factor this time is 0.75. So we can have it as Pu equal to P multiplied by the P sub n. Or again, so we can accept values that are less than or equal to P multiplied by the P sub n. So having 0.75 as our reduction factor. Then for the ASD, our P allowable should be equal less than or equal to the P sub n divided by your factor of safety. Okay, so that is for the tensile rupture strength, or we can abbreviate this one as the TRS, the tensile rupture strength. Then we have for the third one, this is for the block shear strength. So we have again an equation for the nominal strength and the design strength. So as you can see, when it comes to the TRS and the block shear strength, we have the same factors. So factor of safety and the reduction factor for ASD and LRFD respectively. So hopefully we can have an example for each of these cases. So we have the GSY, the TRS, and the block shear. Okay? So this is our introduction for the procedures and methods for the design method for a tension member. So let's have an example. Okay, for our first example, select the lightest W10 section that will resist the given loads. So the member is 7.5 meters long and is assumed to have one line of holes in each flange and two lines of holes in the web. Assume there are 4 bolts in each line, 75 millimeters on center. So from the problem, we have one line for each flange. So that is one on this left side, second on the lower flange, we have 3 and 4. So one line per flange. Then 2 lines for the web. So this is for the web. We have 1 and 2 lines. Then according to the problem, we have 4 bolts in one line, 75 millimeters on center. So these are on centers, 75 millimeters apart. Then the bolts 1, 2, 3, 4. 4 bolts per line. I use a 992 grade 50 steel and 20 millimeters diameter bolts. So our dead load is equal to 780 kilonewtons. Live load is equal to 1,200 kilonewtons. Okay, so use both ASD and LRFD methods. So according to this problem, so for this example, we are to neglect block shear. So we proceed with our solution. So again, this is the cross-sectional area, the one on the left, and this is the side view, our figure on the right. So for the properties of A992 grade 50 steel, so Fy is equal to 50 KSI, that is in kips per square inch, but in the Philippines, we usually use megapascals, or this is the newtons per square millimeters. So if we are to convert, for example, we can have 1 KSI is equal to 6.895 megapascals. So let's try to convert and check. So let's say that is 50 multiplied by 6.895. That is 344.75 megapascals, or rounded to 345. Then for the 65, this is 65 multiplied by 6.895. That is 448.175. Then rounded to 448 megapascals. Okay. Then according to the problem, we are to use the diameter of the bolt to be used is equal to 22 millimeters. But for from ASC, so what will be the equivalent nominal? The nominal diameter of the hole. So it can't be the same as 22 millimeters. So from ASC, so we are to add 2 mm. So the given diameter is 22 millimeters, but we are to add 2 millimeters. So from AISC, the diameter of the hole should be 2 mm more compared to the diameter of the bolt. So we'll be having 24 millimeters. But again, what will be our net for the net diameter of the hole? So that will be equal to 24 millimeters. So this time, another plus 2 mm. So this is from the NSCP provision. Okay, so you can check that class in, I think, chapter 5 of our NSCP 2015. So the net diameter of the hole will be equal to 26 millimeters. So some designers directly add 4 mm for the final diameter of the hole, that will be 26 millimeters. But for this case, just to clarify, so this is plus 2 is from AISC, then plus 2 from NSCP 2015. So this will be we are to use use the diameter of the hole to be 26 millimeters. And then when it comes to our loadings, or for the load combination, so we are to consider the two method according to the problem. The first one is the LRFD. For the load combination, or for the ultimate load, we have two considerations. That is 1.2 of the dead loads plus 1.6 of the live loads, or we can have it as 1.4 of the dead loads, whichever is higher. So let us check. Again, the given dead load is equal to 780 kilonewtons. Then the given live loads is equal to 1,200 kilonewtons. So let us check these values again. So 780 N 1,200 kilonewtons. So let's have the PU is now equal to 1.2 of the dead load. 1.2 of 780 kilonewtons plus the 1.6 of 1,200. So we have PU using the first combination. This is 1.2 of 780, then plus 1.6 of 1,200. That is equal to 2,856 kilonewtons. Then for the other load combination, PU is equal to 1.4 of 780 kilonewtons, and this is equal to I think this is expected to be much lesser. That is 1,092 kilonewtons. So whichever is higher, this one will govern. We are to use 2,856 kilonewtons. So that is our for load combination under LRFD. Well, for ASD, we have only one load combination. The ASD, that is the allowable load. PA is simply the dead loads plus the live loads. So we will be having 780 kilonewtons plus 1,200 kilonewtons. The allowable load will be equal to this is 1,980 kilonewtons. We are to use this under the ASD. So is that correct? So this 780 plus 1,200, 1,980 kilonewtons. So we can now proceed to our considerations. So we have the GSY and the TRS. So gross section yielding and the tensile rupture strength. So for the first one, so this is for the gross section yielding. So we are looking for the section lightest W10 section. So let us first determine the required minimum gross area of the section. Then later on, we compare that value to our table. So we have for the gross section yielding under the LRFD. So we have this is the PU is equal to P multiplied by the P sub n, or again for our equation should be less than or equal to P multiplied by P sub n, or less than or equal to P, a reduction factor, multiplied by Fy, then multiplied by the area gross. So if you are looking for the area gross, that is the ultimate load, divided by our reduction factor, the reduction factor P multiplied by Fy. So what is our PU under LRFD? That is 2,856 kilonewtons. So let's have it as 2,856 kilonewtons. So our reduction factor for tension, again, that is P is equal to 0.90. So this is divided by 0.90. Our Fy is 345 megapascals. Okay? So this is 345 megapascals. So if we are to do unit analysis, 345 is newtons per square millimeters. So our numerator is in kilonewtons, so we have to multiply this one by 1,000 newtons is to 1 kilonewtons. So let's have the area gross under LRFD GSY. This is 2,856 multiplied by 1,000 to be divided by 0.9 by 345. So we have the required area is, so I'll be just using the whole number since 0.067 and it is in millimeters already. That is a very negligible value. So 9,198 square millimeters. So again, I'm just using the whole numbers for a reason. 0.067 square mm is very negligible. Okay, that is for the LRFD. Then for the ASD, we have the PA, the allowable stress or the allowable force. I should be less than or equal to the P sub n divided by the omega. So for tension members, the value of omega is equal to 1.67, the factor of safety. So this is the same as P sub A is less than or equal to Fy multiplied by Ag divided by the omega. And so if we are looking or computing for the Ag, that is equal to the allowable load multiplied by the omega divided by the Fy. Okay, so computing for the area, gross area under ASD, so we have Ag is equal to PA. What is our PA a while ago? That's 1,980 kilonewtons. Okay, so we have that as 1,980 kilonewtons. This is to be divided, multiplied by 1.67 divided by Fy is 345 megapascals. That is the same in unit newtons per square millimeters. So again, for consistency of units, we are multiplying 1,000 newtons is to 1 kilonewton in the numerator. So you have Ag is now equal to the gross area under ASD, 1,980 multiplied by 1.67 to be divided by 345. Then multiplied by 1,000. That is 9,584. So I'll be just using the whole number again. 9,584 square millimeters. If you are to do unit analysis, cancelling newtons, kilonewtons, so the remaining area is square mm. So if our reference is under GSY, so the governing area should be 9,584, okay, under ASD. So this is the safer area. Okay, so that is for GSY and ASD. GSY for LRFD and ASD. So let us check for the second one, the TRS, or that is the tensile's rupture strength. Okay, so for our second consideration, that is for the tensile rupture, and the tensile rupture strength. So we have for under LRFD, what is the equivalent of PU? PU should be less than or equal to P multiplied by P sub n. or we'll be having less than or equal to the P multiplied by FU multiplied by AE, wherein the value of P for the tensile rupture strength, that is equal to 0.75. So how do we compute for this AE? We can have PU is equal to, we have P multiplied by FU. This is the same as the area gross multiplied by the shear log factor U. So what is the value of our shear log factor U? So we have this, again, also for from our NSCP. I think this is chapter still, for steel design, chapter 5. What will be the value of the shear log factor? Alright, so for connections, so we are to use this case, that is case number 1. All tension members where the tension load is transmitted directly to each of the cross-sectional elements by fasteners or welds. So we are to use U is equal to 1.0. So simply equal to 1. So that will be the equivalent of AE. But again, since we are to consider the areas of the holes, we have PU will be equal to P multiplied by FU. Our total area should be the area gross minus the all areas of the holes. Multiplied by this shear log factor. So if we are computing for the area gross for under total tensile rupture strength, we have the area gross is now equal to, I'll be just manipulating this equation, that is PU divided by P FU, then the shear log factor U. Then if I transpose this negative area of the holes, that will be plus, or the area of the holes. So when it comes to the tensile rupture strength, the TRS, one problem is that we don't have yet these properties, the areas of the holes. For a reason, we don't have yet a section. So if we are to go back on our problem, so we are to select the lightest W10 section. We are to select the lightest W10 section. So we are to proceed on a table. I think this is a table provided by a manufacturer. But we can have also the copy of this table from ASC. They are downloadable files. So we are to select the lightest W10. So this is in imperial. The name is in imperial units. It is W10 by 10 by 49. So by description, it is inches by inches, then it's weight or mass. So a width of 10, a height of 10, a width of 10 inches, then 49 pounds per foot. That will be the mass. But its corresponding values for the properties are in millimeters and square millimeter. So the lightest when it comes to the W10 section is W10 by 10 by 49. That is, it has a mass of 73 kilograms per meter. Okay, on this column. So 73 kg per meter. So we can have it as our trial section. So let's have a trial section. So our trial section will be the W10 by 10 by 49. Okay. So its properties, we need its properties, the thickness of its web and the thickness of its flange. Okay, so let's have the properties. Okay, the thickness of the web of W10 by 10 by 49 is 8.6. And the thickness of the flange is 14.2. So thickness of the web is 8.6 millimeters. and the thickness of the flange is 14.2 millimeters. So what are those holes, or what are the areas of the holes? Okay, for this one. So that area of the hole is the same as, we call it sometimes as the bearing area. Okay, for the bearing area, that is basically the thickness multiplied by the diameter of the hole. Okay, for example here, for our trial section, the thickness of the flange is 14.2. And the thickness of the web is equal to 8.6. So for example, this portion, what is the area of that portion? The bearing area. So its equivalent is an area of a rectangle. It has a width of the diameter of the hole multiplied by its height, that is the thickness of the flange. So the same with this one. For the web. So for the web, what is its height? That is the same as the diameter of the hole. Divided the diameter of the hole and a length of the thickness of the web. Basically, we have areas of rectangle. Again, I think from our strength of materials, we call them as the bearing area. So we have 4 on flange. So 4 areas on flange. So again, 1, 2, 3, 4, or both flanges, and 2 areas for the web. So if we were to write that in an equation, so this is the same as the area gross is equal to the P sub u divided by P divided by Fu. P multiplied by Fu by the shear log factor, plus we have 4 for the flange or flanges. That is for the diameter of the hole multiplied by the thickness of the flange. Then on the web, we have 2. That is 2 multiplied by the diameter of the hole multiplied by the thickness of the web. That's how we write it in terms of an equation. Again, so what is our shear log factor for this case? Assuming that the load will be distributed to all fasteners, that will be equal to 1.0. So let us compute now for the area gross using this trial section. The W 10 by 10 by 49. Again, what is our net diameter of the hole? A while ago, we have it as 26 millimeters. So the required area gross under tensile rupture strength is now equal to PU LRFD 2,856. 2,856 kilonewtons. So we are to multiply this one to be in newtons. Divided by P for tensile rupture strength, or TRS, it's 0.75. Then our FU, what is our FU? Where will go? The value of FU is 448 megapascals. So this is 448 megapascals. Shear log factor is 1.0. Then plus 4. Diameter of the hole is 26. Thickness of the flange is 14.2. Then plus 2 times the diameter of the hole, 26. This is for the web. Thickness of the web is 8.6. So this will be the required gross area under LRFD. This 856 multiplied by 1,000 to be in newtons, divided by 0.75 of 448. Then shear log factor, that is 1. Then plus 4 times 26, multiplied by 14.2. Plus twice of 26 by 8.6. That is, our required area is 10,420 24 square millimeters. So if we are to base both TRS and GSY, then we can tell that we are neglecting GSY already, since they are smaller compared to the required gross area under TRS. This is the required area under TRS. So what about for the ASD? But before we proceed to ASD, let us compare this area, the required area under LRFD for TRS, to the actual area, gross area of our trial section. So let's have the gross area for our trial section. For the W10 by 10 by 49, its gross area is 92.9, but based on its unit, that is in terms of the square centimeters. So 92.9 square centimeters. So this is the area gross is 92.9 square centimeters multiplied by 10 mm is to 1 cm, then squared. So I think this is obviously equal to 92.9 multiplied by 10 squared. That is 100. We have 9,290 square millimeters. So basically, the required gross area is greater than the actual area of our trial section. So which means this W10 by 10 by 49 is inadequate. It's not suitable for the design. But before we proceed to another section, let us check for ASD first. So this is for the ASD. We have this is the P allowable is the P sub n divided by the omega, and the value of omega this time is under TRS is 2.0. So we have PA is equal to FU multiplied by the area E. Area E divided by the omega. Then we can have the allowable force is now equal to FU. A is our multiplied by the shear log factor. Then area gross minus the area of the holes divided by the omega, the factor of safety. So if we are to equate this one to the area gross, if we are to manipulate this equation, the area gross is equal to PA multiplied by omega divided by FU multiplied by the shear log factor U. Then if I to transpose this area of the holes, that will be plus the area of the holes. Then computing now for the area gross for ASD. So the allowable force a while ago is that's 1,980 kilonewtons. That is in terms of newtons to be multiplied by 1,000. Then factor of safety is 2.0. FU is equal to 448 megapascals. Shear log factor is 1.0. Area of the holes, that is similar to our area of the holes from the LRFD a while ago. So that is 4 times 20, 4 holes for the flanges, and 2 holes for the web. So supposedly this is plus 4 times diameter of the holes 26, thickness of the flange is 14.2, plus twice diameter of the holes 26, thickness of the web is 8.6. So computing for the required gross area under ASD. This is 1980 multiplied by 1000 to be newtons times 2. This is divided by 448. Then plus 4 times 26 multiplied by 14.2. Then plus twice of 26 to be multiplied by the thickness of the web, that is 8.6. So the required area is 10,000. I'll be just using the whole numbers since they are just our reference. 10,763 square millimeters. So, okay, a close value to our required area for AG, LR, FD, 10,424. So therefore, if you are to base gross areas, we are just considering TRS since these areas are much greater compared to the areas under GSY. So let this be the areas as our reference areas. Okay, the area under LRFD and ASD for the analysis. Okay, tensile rupture strength. So we are to look for a section with a greater area compared to this value. Okay, so we go back to our table. The required area is 10.7 for ASD and 10.4 for LRFD. So the next lightest is 10 by 54, but inadequate, 10,200. So I think the most economical section to be used will be this one, the W, 10 by 10 by 60 with an area of 114. So let's try is W10 by 10 by 60. So let's have the properties. The thickness of the web is 10.7 millimeters. The thickness of the flange is equal to 17.3 millimeters. Then its gross area is equal to 114. Take note, its unit is in square centimeters, so multiplied by 100, that will be 11,400 square millimeters. Okay, so these are the properties. So this area is greater than the required area under TRS. So 10,400 and 10,700. But okay, so using this section, let us check its adequacy. Okay, so let's check its adequacy. So we have, let's have the PN. PN is basically equal to the FY times the area gross. So we have for PN, Fy is, a while ago, it is 345 megapascals, the newtons per square millimeter. Area gross for this W10 by 60, that is 11,400 square millimeters. So if we are to do unit analysis, cancelling Newton square mm, the remaining unit is newtons. So to be multiplied by 1 kilonewton is to 1,000 newtons. So we have the nominal load is now equal to 345 multiplied by 11,400, to be divided by 1,000. So the nominal capacity or nominal strength of our trial section is 3,933 kilonewtons. So let us recall what is our PU. Our PU is 2,856 kilonewtons. Our P allowable is 1,980 kilonewtons. So let us just check its adequacy under the two methods. So this is under LRFD and under the ASD. So for a safe design under LRFD, the PU should be less than or equal to the reduction factor multiplied by the P sub n. So what is our actual ultimate load? That is 2,856 kilonewtons. Is it less than or equal to P 0.9 of the capacity of this section? That is 3,933. So we have 2,856. Is it less than or equal to? Okay, check. So this is multiplied by 0.9. That is 3,539.7. 3,539.7 kilonewtons. So this is safe. Okay, in terms of LRFD, it is adequate. Okay, since the ultimate load is less than, what is that value? 39. So 3,539.7. So again, so the ultimate load, actual load is 2856, is less than, okay, 3539.7 under LRFD. Okay, well, for the case of ASD, we have P allowable is less than or equal to the nominal strength divided by the factor of safety. So we have the allowable is 1,980 kilonewtons. Is it less than 3,933 divided by omega for tension is 1.67. And okay, we have 1,980. Is it less than? Or we say less than or equal to. So that is 3,933 divided by 1.67. 2355. So 2355 2355.09 kilonewtons. So it is also adequate and safe under ASD. So this is for if you are considering the gross section yielding. Okay. So let us check TRS. Okay, so let's try TRS. So for the TRS, so this is the nominal strength, P sub n, is FU divided by AE. Or this is the same as P sub n is FU multiplied by the shear log factor, then multiplied by the area gross minus the area of the holes. So when it comes to the area of the holes, we need the properties of our trial section. So for the web, we have two holes. Okay, with a thickness of 10.7. Then for the flanges, we have four holes with a thickness of 17.3. And if you are to recall, the net diameter of the hole is 26 millimeters. So let's have the nominal strength is equal to FU. Recalling that value, that is 448 megapascals. Shear log factor is 1.0. Gross area of our trial section is 11,400. Is 11,400 square millimeters minus area of the holes. 4 holes for both flanges, top and bottom flanges. That is with a diameter of 26 millimeters. Then the thickness of the flange is 17 point. Again, what is that value? Is 17.3. Then to be minus 2. Diameter of the hole is 26. The thickness of the web is 10.7. So let's have the nominal strength. This is by TRS, the tensile rupture strength. This is 448 megapascals multiplied by 11,400 minus 4 times 26 by 17.3. Then minus 2 times 26 multiplied by 10.7. This is in terms of kilonewtons, by the way, newtons. So we are to convert this one to kilonewtons. So 1 kilonewton is to 1,000 newtons. So this value is in newtons divided by 1,000. So for 4,051.89 kilonewtons. Then again, we are considering LRFD and ASD. So this is for LRFD. Again, reminder, this is under TRS. So we have the PU should be less than or equal to P of the nominal strength. So this is 2,856, I guess. 2856, is it less than or equal to 0 point? TRS, our reduction factor is 0.75. 4051.89. So this is 2856. I think this is less than this value multiplied by 0.75. That is 3038.92. Okay, so we can conclude that it is safe and adequate. Okay. Then for the ASD, we have the allowable. It should be less than. It should be less than or equal to the nominal divided by R omega. So we have the allowable is 1,980 kilonewtons. Is it less than or equal to 4,051.89? So what is our omega under TRS? That is divided by 2. So we have 1,980. I think this is less than. We have 4,051.89 to be divided by 2. The factor of safety for TRS. 2025.945. 2025.945 kilonewtons. So it is the allowable is less than this P sub n over d omega. So it is adequate and safe. So again, that is after GSY, we are able to check its adequacy under the tensile rupture strength. But for this problem, according to this problem, we are to neglect this consideration, block shear. But for the cases that we have, for example, a very long member that is 7.5 meters, we need to check its stability against buckling. So how do we do that? How do we consider its stability? So we are considering, class, this should be the next consideration, the slenderness ratio. For this slenderness ratio, that is equal to the effective length or the unsupported length divided by the radius of gyration. So specifically, we have radius of gyration is the square root of the moment of inertia divided by the area or the gross sectional area of a section. So in some tables, the radius of gyration are already available. But for example, for this case, if it's not available, we can compute that value. Then, so to be stable, we have, based on AISC, the value of the slenderness ratio, the length over R, should be less than or equal to 300. So let us check, for this section, with a length of 7.5 meters, or let's say in millimeters, this is 7,500 millimeters. Okay, so we need to check for both axes, so x-axis and y-axis. Okay, so we have IX. Okay, IX is equal to 14,260 centimeters to the fourth. That is for if you are to observe the unit, that is 14,260 centimeters to the fourth. Again, that is for our chosen section, the W10 by 60. Then for its IY, the IY is equal to 4,841, the weaker axis, centimeters to the fourth. So let us check both axes, the slenderness ratio for both axes. So the radius of gyration for the x-axis is the square root of I. This is 14,260. The area, again, the area of our chosen section is 11,400 square millimeters, or in centimeters, that is 114 square centimeters. So divided by 114. If you are to observe the units, the unit of this term will be in a square, in centimeters, since that is radius. So to be multiplied by 10 mm is to 1 cm. So let's have the radius of gyration, okay, with respect to the x-axis. The square root of 14,260, this is to be divided by 114, is 11.18 times 10 to be in mm, okay, 111.84 millimeters. Then the radius of gyration with respect to y is the square root of 4,841 divided by the area, 114. So again, that is in terms of centimeters. So multiplied by 10 mm, to be divided by 1 centimeter. Okay. So the radius of gyration with respect to y is now equal to the square root of the weaker axis, 4841 divided by 114. Then multiplied by 10. That is 65. You have 65.165. Okay, so 65.165. Then let us now check the slenderness ratio, let's say for the x-axis, that is the length, 7,500 millimeters, divided by, what is our Rx? 111.84. And this is equal to 7,500 divided by 111.84 is equal to, we have 67.06. This is obviously less than 300. So we can conclude that it is adequate. Then, the slenderness ratio along the y-axis is equal to 7,500 divided by our Ry. Ry is 65.1, 65. And this is now equal to we have 65.165 is 115.09, 115.09, and also less than 300. So therefore, so both axes, the slenderness ratio is adequate. So we need to consider the slenderness ratio, if we have a very long member. So that is 7.5 meters. So we can now conclude that we are to use the section W10 by 10 by 60. This will be the required the wide flange to be used. So this is our entire solution for this example.